So we have one more section to talk about with buffers. This last part is kind of about, some of the finer points. Buffer capacity. Okay, so the amount of protons or hydroxide ions that a buffer can absorb is the buffer capacity. And that goes right back to how many moles of acid and conjugate base you have in your buffer system. Okay, so a larger concentration of HA and A minus would result in a higher buffer capacity, i.e., more moles of acid, more moles of conjugate base, the more moles of the strong acid or strong base you can react with it before you use up all the buffering action. Okay, so a buffer is going to have, the pH is determined by the pKa of the acid. So a buffer with a small capacity, well, it still works as a buffer, it just doesn't last as long. Okay, because so it just doesn't allow you to add as much acid or base without a significant change. Okay, so we're going to, in this example, we're going to compare the acetic acid acetate buffer from the previous section. We're going to compare 5 molar concentration of the buffer versus a 0.05 molar concentration. Now, both of these buffers are going to have the same pH to start with, because they have equal amounts of acetic acid and acetate ion, okay? And they both they have the same pKa, and so at first glance they look identical. Okay, the only difference is how much acid or base you can add before the pH goes kablamo, like wah. Okay, so here's our Henderson-Hasselbalch equation. So pH equals pKa plus the log of the acetate ion over the acetic acid concentration. Okay, so in each solution, they're equal to each other, so the pH is going to be equal to the pKa for both of those. Okay, so far so good. Now, I've lost my place. Okay, here we are. We're on page 5 of the notes handout. All right, so the first one says we're going to add a 0.01 mole of gaseous HCl. So in other words, we're just adding HCl straight into the system, okay? And we're going to figure out what happens. Okay, so when we add the H+, this shouldn't be an equilibrium. This should also be a one-way arrow. I got to go back and fix this PowerPoint. Okay, we're going to react 0.01 moles of H+ with our 5 moles, because we have 1 liter of solution, so we know we have 5 moles, okay? So after the reaction happens, all the moles of H+ are used up, and that determines how much of the other things react. So it goes down by 0.01 moles, and then our HA goes up by 0.01 moles. Because remember, when you add a strong acid, it's going to react with the conjugate base in the buffer system. Now, if we plug this into our Henderson-Hasselbalch equation, we have a pH of 4.74. Really, no change, okay? Because the buffer capacity is so high, this change in the amount of HA and A minus is insignificant in terms of the calculation. Now, we're going to do the same thing again, but this time we're going to start with 0.05 molar, 1 liter of a 0.05 molar. So we have 0.05 moles of the acetate ion, and we have 0.05 moles of the acetic acid in our buffer solution. And we're going to react it with 0.01 moles of H+. Okay, so again, here's a stoichiometry of our reaction. Minus the H+ is our limiting reactant. So the H+ is going to react with the conjugate base, and it's going to go down by 0.01. And the HA is going to go up by 0.01. Okay, now we're going to take our after concentrations and put them into our Henderson-Hasselbalch equation. So now, because this buffer has a smaller capacity, that same amount of HCl added to it has a bigger effect on the system. okay? Because solution A has a high concentration of the acid and conjugate base, it's able to withstand change in pH much better than this one, which has a low concentration of acid and conjugate base. Okay, it just goes to reason. All right, how do you know what buffer to choose? We touched on this just a little bit in class. Okay, so the optimal buffer is the one that you can set up where you have equal molarity of HA and A minus. And so that way we can use the pKa to choose the closest possible pH. Okay, since the pH is equal to pKa when the acid and conjugate base are equal to each other, the buffer system, the pH of the buffer system is going to hover right around the pKa. So if you figure out what the pKa is, that's going to tell you where the buffering action is going to happen for that system. Okay, so for example, whoopsies, I gave you the answer before. If you need to know, if you want to make a buffer system that has a pH of 4.3, right on the nose, okay, from one of these acids, first thing we're going to do is calculate the pKa of all the acids, okay? So if we know the pKa of all of these acids, we can figure out which one's going to get us closest, all right? So all right, this is not how I would do this problem. First thing I would do is calculate the pKa of all of them, and then figure out which one was closest, and then figure out the ratio of HA to A minus. Now, theoretically, you could actually make a pH, a buffer of 4.3 from all of these, all right? It's probably going to be easiest from benzoic acid or propanoic acid because their pKa's are probably going to be closest to 4.3. Okay, and if you notice benzoic acid, the ratio of HA to A minus is closest to 1. So that's probably the best one to choose because it's the closest. And then by making a little bit of a tweak of the HA to A minus concentration, you can then go back and figure out how to make that buffer specifically. Okay, so the take-home message here, use the pKa to get close to the pH, and then from there you can figure out the optimal ratio of HA to A minus. That'll get you right on the nose for the buffer system you're looking for. Okay, well, we're going to practice more of this. There's a mysterious page after page 20 in your notes. It has no number. And no, it's snuck right in there between 20 and 21. So it has at the top, Dr. White, worksheet 8, buffers, answers at the end. Ha ha ha. All right, so I want you to go through and try those problems. It's not labeled as a practice set. I think I just decided to add it in and then I didn't revise the numbers. Okay, so these are the sneaky pages between 20 and 21. What would we call it? 20.3 and 20.6? I don't know. Anyway, take a look at that and have it ready to go for class when I see you.